In this video, we'll be covering optimization in regards to a rectangular plot, or in any case, some form of a rectangular object. In this case, a rectangular plot of farmland will be bounded on one side by a river and three sides by a single strand of electrical fence. So in terms of any of these problems, if it is a image or geometric problem, we're going to go ahead and draw ourselves a picture. So, and you'll notice here I have a rectangular plot of land, or a rectangle, where on one side it's bounded by a river, and the other three it's bounded by the fence. With 800 meters of wire available, meaning that if I have here, here, and here all added up, if I have the perimeter of this setup, the perimeter should be equal to 800 meters, and that should be equal to, well, in this case I should probably label these unknown values. Well, this is a distance in terms of looks like x, so I'm going to call that x. I'm going to call this y, and therefore this side over here is y, because this must be a rectangular plot. So in that case, the perimeter of these three sides, and again it's only the three sides because this doesn't have electrical wire on it. So the three sides added together, y plus x plus y, is x plus 2y, and that's equal to 800 meters. Again, notice with 800 meters of wire available, what is the largest area that can be enclosed, and what are the dimensions? Now notice in this question, it is what is the largest area, so I want A equals when I'm all said and done. Secondly, that can be enclosed, and what dimensions are there. So I'm going to need to have x and y as a final solution. Not just A, not just x and y, but all three, because of the way the question is worded. So I'm going to go ahead down here. This right here, you'll notice, if I ignore this p-value, 800 equals to x plus 2y. This is what we call our restriction equation. Again, that is the thing that limits our variables. The second piece I've got to figure out is what is the optimization equation. Well, the thing that we want to find the largest or smallest value of is area. So the area is x times y, and this is our optimization. In which case, if I have an optimization and a restriction equation, I will take the restriction equation, I will solve it for one of the variables, and I will plug it into the optimization equation. So down here, if I have 800 equals to x plus 2y, the intent is to solve for one of these two variables, in which case, again, I can solve for x, or I can solve for y. It won't matter which one, it's whichever is easiest to solve for, and whichever one is easiest to plug back in here. In this case, I would argue that solving for x is actually easier than solving for y, in which case, because I'd subtract x, I would have to divide by 2, and then I'd have a fraction in this problem. In which case, for solving for just x, I can go ahead and have x equals 800 minus 2 times y. Again, there's nothing wrong with setting this equation up this way as long as I solve for one of the variables. I can then take this restriction equation and plug it into my optimization equation. So down here, combined with this information, I will have the area function is actually equal to x, which is 800 minus 2y, which I will replace x with 800 minus 2y, times y. In which case you'll notice I now have an equation that is optimization equation of a single variable y. I'm going to go ahead and multiply this out. Again, use some algebra to simplify the function. So it's very easy for me to take the derivative of that. Again, the reason why I have to take the derivative of this is because the optimization will always occur where the derivative is equal to 0. So I'm going to take the derivative, and that's going to be equal to, and over here, derivative of 800y is just 800. There is no need for a dy dx because we are taking the derivative of this function in respect to y, because the variable that we have in this equation is y. So that's 800, the derivative of y in this case is 1, minus the derivative of 2y squared is 4y. Again, no more dy dx's, because we are taking the derivative of y in respect to y. So now I have this right here, and all I have to do is solve for y, and that'll provide me with the length of this side here. Then I'm going to have to find this side here, and finally, again, don't forget we have to solve for the area. So in this problem, I'm going to go ahead and subtract the 800, giving me a negative 800 is equal to a negative 4y. I will divide by negative 4, and that will provide me with y is equal to 200. And again, let's be very careful with our units. In this problem, the measurement that we're playing with is all in terms of meters. So I'm going to go ahead and make sure that this is designated as meters. So in my final answer over here, I'm going to write 200 meters. After I've found y, again, the way that we're going to find x is by taking this y value and plugging it back into the original the original restriction equation. Again, the original restriction equation. So when I plug 200 back into here, that's going to give me 2 times 200. I'm going to write that over here. I have 800 equals to x plus 2 times 200. Solving this equation, I'll subtract 400 from both sides because 2 times 200 is 400. I will get x is equal to 400. So this provides me, again, 400 meters, and that's my answer for this piece. Lastly, you can do the last optimization, or again, what is the largest area in this last step, simply by either A, multiplying these two pieces together, or B, taking one of these values and plugging it back into the area equation that we solved for in the beginning. So I'm going to go ahead and say, well, my area equation is nothing more than x times y. So x times y is 2 times 4 is 8, and I have 4 zeros behind it, and that's meters squared. Again, meters times meters is meters squared. That provides the answer to this problem, such that, again, the area of this block of space right in here is 80,000 meters, and then this distance here is going to be, again, 200 meters, where this distance is 400 meters.